Okay, welcome everyone to this bi-monthly CDAC webinar. Unfortunately, we missed the last one because of a cancellation, so this is the first one this month. Today, I'm pleased to introduce one of our longtime CDAC collaborators, Tadashi Ogitsu from the Quantum Simulation Group at Livermore. Tadashi is an expert in quantum simulations, including studies of low Z materials at extreme conditions, but more recently has moved into areas such as materials for energy storage and conversion, including photoelectrochemical hydrogen production and storage. Tadashi has a PhD in material science from the University of Tsukuba, which he received in 1994, and he was a research associate at the Institute for Solid State Physics at the University of Tokyo before becoming a postdoc at UIUC and joining Livermore in 2001, just 2 years before launch of CDAC. And he's been active in the CDAC program ever since, collaborating with numerous partners over the years. And I think today will be sort of a retrospective on some of his work at Livermore. So thank you very much for agreeing to give this talk.
Thank you for introduction, Russ. And actually, in a way that Russ, you are the person that who introduced me to high pressure physics back in, I was in Japan. And I'm glad to be back here and give a little bit of a presentation about high pressure physics research that I got involved in it, as well as recent my activity at Lawrence Livermore National Lab. Let me start from this that probably not that many people know very well about, let's say, like a location and the background of Lawrence Livermore National Lab. I'm not going to go in too much detail, but basically it's in the Bay Area, but basically east of San Francisco or San Jose or Berkeley, about 1 hour from those sort of like well-known locations in the inland. Climate-wise, it's quite a bit different that unlike San Francisco, that in the summer that we get something like 110 degrees in the summer. So that's a little bit different. And then the lab was established in 1952 at the height of Cold War to meet urgent national security needs by advancing nuclear weapon science and technology. That's sort of like a statement I copied from Livermore's official web page. Is a very famous Nobel laureate, Mr. Lawrence and Edward Teller, and first the director discussing each other. And then this is recent information that what is known for Premier Research and Development Institution for Science and Technology applied to national security. That's from Wikipedia, but that's something that if you recall presentation by Kim Wooddill, that's sort of like a general statement made, a little bit more broader than just weapon science and technology, which was initially started. And recently, I found a very interesting book published by a former lab employee named Tom Ramos. The title of the book is From Berkeley to Berlin, and some of the explanation or some trailer kind of thing is found at his blog post here in the shown. He knows very well about the background and summarized about some physics history behind Livermore Labs. That's quite a fascinating story, so I highly recommend it to read it. So one of the important things that I wanted to talk before going to scientific discussion is that, as I mentioned earlier, that I used to work quite a bit on high pressure physics, but not that much anymore. And what's behind the scene, which is something to do with this Livermore Labs transition, which took place in 2008. Before that, we were explained by the management people that that's how they basically thought about how Livermore Lab should be transformed into. Basically, the Livermore Lab is under National Nuclear Security Administration, and which has a sort of like more weapon-oriented researches. And now even back then we had quite a bit of basic science, but after the transition by 2025, what the management people aimed for is that this is sort of like excellence. This axis corresponds to excellence in activities, and either basic science, more general science, or Livermore program. We would like to make it to this as far as we can. And only the difference is that before the transition, basically Livermore Lab paid pretty much all the scientific activity. While after the transition, researchers are sort of like responsible for the getting external funding to support basic science. I would assume that typically from Office of Science of US Department of Energy, such as like a basic energy science or fusion energy science, which is kind of like interesting in that this is right side is a relation to temperature pressure phase diagram and this statement, because low pressure and low temperature side is typically supported by BES, Basic Energy Science Office program of US Department of Energy, while NNSA's mission is much, much higher pressure and temperature. And the Office of Science, Fusion Energy Science also focus on this area of research. So there is certainly an implication that if you're working at the NNSA lab and would like to continue high pressure physics, we have to get funding support from somewhere such as BES, but BES is not particularly focusing on high pressure physics, which is sort of like related to the situation that took place in my research activity, history of my research activity. So my research activities in the quantum simulation group at the group at Lawrence Livermore National Lab. This work is before the joining Livermore Lab, but it was kind of like an important one, so that I included it. I joined the Livermore Lab in June 2001. And right before that, I worked on the high pressure phase of hydrogen and published one paper on proton quantum distribution of solid hydrogen on Nature. And last wrote a really nice introductory article on the same issue. And then after joining lab, we for a while, I myself, for a while, focused on the high pressure physics, such as phase diagram of carbon dioxide or lithium hydride or hydrogen, and then the boron and a few other systems. And then simultaneously, this was a sort of like a top-down project, but I was sort of like asked to provide theoretical support to ultra-fast science in warm dense matter physics, or the no equilibrium gold earlier on from 2003 to 6. And then the subject switched to kappa. I'm going to explain a little bit why it happened. And then later in Ireland, and the project ended around 2020, and we don't know that what's going to be the next, which is related to facts that this is mostly supported by fusion energy science, but we do not have, or I myself do not have support from fusion energy science. Meanwhile, high pressure physics activity went down quite a bit, but continued as a CDAC collaboration, mostly with Eva Zurek of SUNY Buffalo. Meanwhile, after 2008, as I explained, so I needed to sort of like make effort in getting external funding, and the first sort of like available one, was successful one, was hydrogen production research supported by Energy Efficiency and Renewable Energy Office of DOE, under which there is a Hydrogen Fuel Cell Technology Office. And my activity shifted more toward hydrogen production, as last explained. Over the time, things changed, which I'm going to explain briefly. And then from 2019, we started to work on software development of ab initio, basically time-dependent density functional theory software development supported by a basic energy science program of US Department of Energy. First work, very brief explanation, but right before we started this quantum distribution of proton research using the first principle path integral molecular dynamics simulation, there was a very interesting, intriguing publication from this involves the last, I guess, about the phase diagram of solid hydrogen. Back then it looks way simpler than now, but nevertheless, at that time, people knew that there are three sort of like main phases called phase one, which was very sort of, this is very short-handed explanation, but the quantum free rotor hydrogen molecule. And then the phase two, which is a little bit higher in the pressure, is proposed in this paper that the quantum orientational ordered phase. And then the phase three, which is above 150 gigapascal, is described as a classical orientational ordered phase. So this was a sort of like the conjecture came from various observation on the experimental measurement on the vibrational frequencies and such. And so we decided to look into this possibility using this first principle path integral molecular dynamics simulation method, which is basically combination of density functional theory-based molecular dynamics, and which is applied to electronic degree of freedom, and the path integral is applied to nuclear degree of freedom, so that quantum distribution of proton can be simulated properly. And we did relatively sort of like a simplified simulation at representing pressure at 120 GPa, 300 Kelvin, and 120 GPa, and 80 Kelvin. So that should correspond to like this area, crossing this phase one and phase two. And then the 180 GPa, 100K. So it's about this area. And somewhat we managed to sort of like reproduce qualitatively this conjecture that phase one is quantum free rotor, which this is not really perfect because of a limited simulation time. But nevertheless, if you compare those three phases, you can see that orientational distribution is more homogeneous in the phase one condition, while in the phase two, there is a clear orientational sort of like a tendency towards a certain direction. However, liberational sort of like a distribution is still quite large, which gets much narrower to phase three at the higher pressure. And those could correspond to this explanation of quantum free rotor to quantum orientational order, and then classical orientational order. One thing I have to note is that this simulation was performed within distinguishable particle approximation. So it's Boltzmann distribution. So in the reality, we know that this phase one is truly free rotational the system consisting of parahydrogen, which is a S-like wave, while phase two, if the temperature is low enough, is presumably S to D transition, so that there are some D-like component into hydrogen, and which makes this localization of distribution. But nevertheless, we are satisfied with sort of like a qualitative explanation, which is consistent with very nice intuitive explanation given by Russ in the same issue. Basically, from the viewpoint of potential energy surface, and you squeeze it, and then the gets a little bit of sharper, so that would lead to quantum localization or orientational distribution. And then right after I joined Lawrence Livermore lab, I started this project with Stanimir Bonev, who once left Livermore lab, but now they're back at Livermore lab and working on high pressure physics those days. Basically, the situation was that there was an experimental publication by those people proposing that they found new phases called phase 2 and 4, which are sort of like described as a gradual loss of molecular character through bending of molecule or association. And we are kind of like in a way that are asked to sort of like validate with density functional theory simulation. And what happened is that we used their experimentally determined structure and optimized the structure and the volume. And what we found is that those structures were not really stable within the density functional theory calculation. And what we found was rather that those phases still molecular phase. And that the interesting thing is that if it was only DFT result that was sort of like a favoring a molecular phase, that may not be compelling enough. However, what we found is that after sort of like a couple of months of exploration about many possibilities, we decided to look into various basically observable, such as equation of states or some vibrational frequency and such, and found that basically our structure reproduce their measured data very well, so that we proposed alternative phase diagram based on DFT simulation result, which is strictly molecular based. Meanwhile, I was working on developing the simulation method to calculate melting line. So this method is called the two-phase simulation method. And before application of this method, generally speaking, the available method was based on the thermodynamic integration, which is very computationally extensive, as well as very tedious work that you have to run many simulations until it converges. So that's sort of like we know it's possible, but it wasn't a popular method. So we decided to try this method, which is very simple. Basically, you generate initial configuration, which is a combination of solid and liquid, which they are in contact with each other. And then they run the molecular dynamics simulation at a given pressure and temperature. And then the basically idea is that molecular dynamics simulation would converge to a stable phase depending on the given P or T. And actually, before the publications, there were a couple of the publications based on the classical molecular dynamics simulation. We are the first one to apply ab initio molecular dynamics combined with this two-phase simulation method. As you can see that this is actually simulation result, but if temperature is said to be higher than melting temperature, we get actually nice liquid phase, and below melting temperature, it gets a very clear solid phase. This right side is this final result. Based on this method, we mapped out melting temperature or melting curve of lithium hydride. This is at low pressure. Our result is maybe 20% lower than the experimental value, but that's coming from a type of exchange correlation functions that we used. Otherwise, our results seem to be very satisfactory. Particularly, the important part is that if we can unambiguously determine the melting point, which we made assessment based on the volume, there is a clear gap as well as a pair distribution function, which also reflects the solid and liquid very clearly. So that was a sort of like an interesting preparation to the next more interesting the research. Many people here are very familiar with this subject matter, I suppose, but some students perhaps not. So the back in the at that time, maybe even today, there was this conjecture that highly compressed hydrogen might become the metallic phase. Initially, the Wigner and Huntington discussed about BCC atomic metallic phase. But and then there is another possibility due to quantum effect that it might become liquid, and it may be the quantum liquid. And that's originally proposed by Abrikosov in 1961, and a bunch of people explored about that possibility, including famous Neil Ashcroft, who passed away very recently. Actually, I became familiar with this theory from Ashcroft series of invited talks. So I was always thinking he's the one that who came up with this idea, but there seems to be some older publication. And then so that's a sort of like a background story. And because of that, there are a bunch of people that who are interested in this figuring out where this quantum liquid state may happen. One of the indirect way to assess this possibility is to calculate the melting line of hydrogen. And then if there is a maximum from where we may be able to extrapolate it to zero temperature to see that where it may be a quantum liquid state of hydrogen. And this publication was in 2003. And the melting line was mapped out up to something like a 44 GPa at that point. Beyond that, there was still, with the technology available back then, they couldn't reach to sufficient high pressure and high temperature to unambiguously determine whether there is a maximum or not. So we applied the aforementioned two-phase ab initio molecular dynamics simulation method to map out the melting line up to 200 GPa, and our simulation result very clearly indicated that there is a maximum somewhere around 50 to 150 GPa, and extrapolation will give us this number 400 GPa as roughly speaking the potential liquid phase of the hydrogen. Simultaneously, there was a theoretical work which we were not aware of it until it got published. Pure theoretical work to evaluate what kind of state could be possible. This is first author is Babaev, and this is the Ashcroft team actually. As a possibility that it could be a metallic superfluid or normal fluid or superconducting superfluid or electric superconductor. Some interesting suggestion was made, and our simulation result indicated that maybe it's around 400 GPa. This is not my work. I kind of like graduated from hydrogen high pressure work, partly due to this funding constraint and the things. And then soon after we learned that Pickard and Nees in 2007 proposed a new phase at a higher pressure. Originally, their intention was to predict phase 3, but they found lots of interesting structure, including this layer of the monoclinic CMCA12 structure at 300 GPa and some other variants. And then if I understand, this phase diagram is one of the latest published by Alex Goncharov. As you can see that it's not as simple as the previous one, which had only phase 1, 2, and 3, but there seems to be potentially different phases in this high temperature area. And then now we have a better understanding about where those exotic states might happen. And then the materials that I worked on to investigate on the phase diagram was beryllium, which was basically motivated by some old the research that was published in conference proceedings. BCC phase, this is the phase diagram of beryllium, and we know that at ambient condition it is HCP, but there was a proposition that the BCC phase might appear right below this melting temperature, which was kind of interesting because knowing that at lower temperature, HCP phase continues as far as the experiment could verify it. So that was a motivation, and then there was experimental effort in looking into this potential BCC phase. However, they couldn't find the state, but it appears that the experiment was very challenging and they couldn't come to a clear conclusion. So it was published only as an internal report. So I work at the Lawrence Livermore lab, so that naturally that the people came to us to see this possibility. And we use basically the combination of quasi-harmonic approximation and some molecular dynamics simulation. And none of our simulation results actually supported this notion that the BCC phase might appear right underneath of this melting temperature. So this is our proposed phase diagram. HCP would continue up to something like a 400 to GPU. Beyond that, there is a BCC phase, which kind of like a curves like this. But however, it would meet at melting temperature, melting point at about 200 to GPa. So the next, how am I doing? 30 minutes. Subject I worked on is a boron phase diagram. I spent quite a bit of time on this problem, which is mostly because of the complication of this system. Left side is the background is this is Death Valley National Park, and those structural model is beta rhombohedral boron from one sort of like a viewpoint. The reason why I picked this background is that boron is tend to be found in a salt deposit, which is sort of like a Death Valley, and there is a city called Boron in that area, and for exactly that reason, they are one of the largest boron ore, the mining place in the United States. And as you can see that the boron is based on the icosahedral and its variant, fused icosahedral and such. And the complication comes from the one of the factors that icosahedral is bad for space filling. Five-fold symmetry is not compatible with translational symmetry. So that sort of like makes it very difficult to fill with the space, which end up sort of like a very complicated structure. And the preferred charge states of those the building motifs are different, which lead to sort of like a combination of anions, but which is not at all not very satisfactory in the counteracting each other. And then this presence of multi-center bond, which enables boron interstitial to becomes very stable at some odd locations. On the right side, this is a phase diagram with some structural motif, which kind of like a parallels to what I said. Most of those relatively low pressure phases consist of the icosahedral, so that there are some properties that are shared in terms of complications, such as some defect site and such. The most importantly, because of some a property of boron, that it is very difficult to map out the phase diagram, so that when my paper was published back in 2013, available phase diagram, if you lay over each other, it looks like this. So ordering is basically the same. That's fine. However, the precise location of this boundary was quite different to each other. For example, beta rhombohedral boron, that is commonly obtained or stable at ambient conditions. According to one research, that it's not actually stable, but metastable. And alpha boron is stable. While other paper they published by the Organov et al. Rather draw line here, so which means that the beta rhombohedral boron is a ground state. By the way, in this paper that they discovered this new phase called the gamma boron, which is also the icosahedral based, so that it exhibits this ionic property that I mentioned earlier. Beta rhombohedral boron crystal, basically it's made of icosahedral and its variant. Because of time, I have to go really fast. And the icosahedral actually prefers anionic states, -2. This fused icosahedral prefers +3 states. If you combine it with only those motifs, we end up -5 as a sort of the preferred states, or that there is a huge hole states. Those are the sort of like known for many years. And what we discovered is that actually this preference of the anionic states sort of like lead to the unoccupied states that correspond to those inter-icosahedral bonding. If we do not have the defects in this system, or in other words, interstitial or vacancy. And one of the states, interstitial states that is experimentally known is that this states position called the B16, which is in the middle of this hexagonal ring connecting icosahedra. And if we insert this interstitial, actually it transforms those bonds, which originally looks like a conventional 2-center 2-electron bonds to 3-center 3-electron bond. So that is very effective in actually self-doping without changing a number of chemical bonds. This is a little bit more detailed, so that I'm going to skip this, but basically the story is the same. Now we have a vacancy form in the fused icosahedra, which is compensated by other type of interstitial, such as B90 and B70, B18. And the very interesting point is that those interstitial experimentally has been known to form this kind of pattern, which is called the expanded conglomeratis, which is if we map this problem to spin problem, because occupation, occupied or unoccupied, could be mapped on the spin up or down, so that we can use knowledge that we already have for the spin Ising model. And actually, for the conglomeratis, there is an exact solution that known in the 1950s. And we found out that actually we can map our boron partial occupancy problem or interstitial problem to conglomeratis. And then this is sort of like a very typical explanation that anti-ferromagnetic Ising model on the triangle lattice is known to be geometrically frustrated, and its ground state is degenerate and disordered. So it's very interesting that the reason why this system seems to exhibit a very high level of the frustration is a combination of this mainframe part, which cannot satisfy electron counting rule, which means the chemical bond is not completely saturated, which lead to lots of interstitial, which end up forming the geometrically frustrated problem that is can be mapped onto spin Ising, anti-ferromagnetic spin Ising model. CDAC collaboration with Eva Zurek group. We had first the summer student from Eva's group back in 2015 or a little bit earlier, and then we worked on the boron carbide equation of states. And our experimenters at Livermore Lab helped sort of like comparing the Andrews equation of states and experiment. Actually, as you can see, experiment at such a very high pressure and temperature condition as beyond 500 GPa, they basically has quite a bit of uncertainty, so that this is sort of like a very good cross validation between the theory and the experiment. And this is a sort of like a very typical NNSA type research project, which Andrew supported, and now he's at Lawrence Livermore Lab. Another recent project is with Katie Hireke. She already, I think, gave a presentation. I'm not gonna go into detail, but novel high pressure phase of boron explored using external opt. This code is developed by Eva Zurek, and we found out lots of sort of like a metastable structures, which may become realized under certain conditions. Non-equilibrium of warm dense matter. So this is a sort of like interesting and important sort of like a background. Left side, I'm showing Donna Strickland got Nobel Prize in 2018 for development of chopped pulse amplification. And with this, basically, we became possible to generate ultra short high intensity laser pulse without destroying amplifying material. And actually, she briefly worked at Livermore Lab to help development of high power laser at Livermore Lab with current director Kim Budil as a sort of like one of the collaborators. And this is right side schematics that of NIF. There are lots of lasers, 192 of them, and then the target chamber looks sort of like a spherical with lots of holes in it. In the middle, we have this target which consists of things called gold hoframs, which is cylindrical shaped, made of gold. And then the inside there is a spherical shaped target material which contains deuterium and tritium. And the laser comes in like this and hit gold, which generate X-ray and which would heat up capsule. And then the outer shell is gonna move outward as it gets heat up very quickly. And then the inside, inner side of shell, as a reaction that goes the sort of like a move inward very fast, which would compress fuel. And if we are successful, which would lead to basically fusion condition. Another interesting thing about the quantum simulation group is that optical system used in the NIF this is one of the major contributors, but Natalia Zaitskova, who actually is in the quantum simulation group, as this introduction described, she's basically expert on the low temperature solution-based crystal growth method, and then they worked for the development of this crystal for the NIF. And the other things that she worked on is the plastic-based scintillator. And the reason why I mentioned is that let's say that you are interested in the coming to quantum simulation group. It's not recent years, but something like 10 years ago, she used to join our group meeting and then ask questions such as, we were able to grow plastic, which is presumably usable for the scintillator, but it doesn't work. And the reason was the behavior was not ordered as expected, and which was something to do with the defect. And she would come to me and ask what could be the possibility. And as a theoretician, we have to help her to sort it out, and which was something to do with the concentration of impurities and its ordering. Anyhow, that was a little bit of a detour, but this is about warm dense matter research that I have been being involved from 2003 to 2020. This is a schematics of experiment that basically we have a target material which was pumped with this high power laser, and then after that there would be probe which could be optical absorption or the X-ray absorption type of the probe, and then there would be a detector here which would get the signal as a function of time, and based on which we can extract some information. And then in our research, we make some assumption which is sometimes described as a two temperature model, and based on which I'm described that what is happening here. Laser hit system which would excite electron so that initially the electron would get lots of energy, and some excited state would be created, which would relax into the thermal distribution so that we can define temperature. It is not super well established, but generally speaking, this relaxation time scale is considered to be about several hundred femtoseconds, so that for the most of the system, we consider that this approximation that this system could be described as a temperature is valid. And after reaching certain electron temperature as high as something like 20,000 Kelvin in this particular example, due to electron phonon coupling, electronic temperature would decrease because energy would be dissipated into the lattice degree of freedom, and eventually the system would reach to equilibrium. And if final temperature goes beyond something like 10,000 Kelvin, then we classified the system as a sort of like warm dense matter, because it happens very quick. during this period, it's not the target is not going to expand, so that this distinguishes from plasma physics, for example. Theory of electron phonon coupling of electron ion non-equilibrium warm dense matter. Basically, as I mentioned, the electron phonon coupling constant is an important parameter that we have to calculate or estimate. And we know that in the condensed matter physics, we calculate phonon dispersion and electronic structure based on which we can define this matrix and calculate electron coupling in this way, that this delta function is energy momentum conservation law in the transition between the electronic degree of freedom and ionic degree or lattice degree of freedom. There was a proposition back in 2008 or a little bit earlier that actually there is another paper, the often called the Wandana paper, but the idea is that if electronic temperature is high enough, which means higher than the Debye temperature, perhaps some fine structure coming from phonon dispersion can be omitted and just put it as a sort of like a constant. And then they use some approximation and come up with this expression, which is density of state squared multiplied by the Fermi distribution function, the derivative of Fermi distribution function with respect to energy, which is basically Gaussian-like shape, and with its width of KBT, which simplifies the problem quite a bit. And based on which, what you can tell, the only interesting part is that if we pick kappa and apply this, the Wandana formula of electron phonon coupling constant, because imagine that you have a Gaussian function with KBT as a width here, and then integrate this function. What happened is that as you increase the temperature, basically this tail start to hit this high density part of kappa D level. Before that, we have only SP level, which has a relatively low density of states. Accordingly, what happened is that the electron phonon coupling constant starts with a relatively small value, and then as soon as KBT gets large enough to pick up this high density, electron phonon coupling constant increase. For something like a nickel, Fermi level is at the top of this very high density part, so that if you apply same argument, it's supposed to behave in this way, that starting with very high coupling constant, as you raise the electron temperature, it decreases. Is it true? That's a sort of like a thing that we got interested in after initial experiment performed by Yuan Ping et al. This was based on actually optical absorption or dielectric constant measurement. Unfortunately, dielectric function is very convoluted physical quantity, so that we couldn't really gain the information about the electron temperature or ion temperature, so that it wasn't super helpful, but based on which we learned a lot, and we came up with this idea that if we use the time resolved X-ray absorption spectrum, we can actually pretty much like a directly measure electron temperature, based on which by comparing with the theoretical model, we can extract, compare experimentally determined electron phonon coupling constant versus theoretical value, which is a line here, based on a choice of density of states, which was very interesting. This dashed line corresponds to theoretical the electron phonon coupling based on zero temperature density of states. If we use high temperature density of states, actually it goes down a little bit. And it seems that the experiment and the theory are consistent in the sense that at lower fluence or lower excitation, the electron phonon coupling constant goes to a relatively higher side compared to theory, while at a higher fluence or higher initial electron temperature, it goes down below this zero temperature based theoretical model, but in agreement with liquid based model. And the next thing was we applied the same platform to iron, which is resembled to nickel. I'm simplifying this argument because iron at ground state is ferromagnetic. In that sense, it doesn't, but we know it, optical excitation would destroy ferromagnetic states. And then with that assumption, basically it becomes sort of like a similar problem with nickel, where we expect this rapid decrease of electron-phonon coupling constant. And actually, experimental measurement agree with this picture that if we do not assume this rapid decrease in the electron-phonon coupling constant, we can't really reproduce experimental X-ray absorption time profile evolution of X-ray absorption spectrum. I'm kind of like running out of time, so I just very briefly mentioned that recent my activity, this is consuming my time about like 55%. The last year, there was announcements from US Department of Energy about the Earthshot, which is about hydrogen production. Reduce cost of hydrogen down to $1 per 1 kilogram in 1 decade by the end of 2030. And in order to do that, they allocated 400 million in FY22, and it's supposed to continue for some time. Hydrogen Consortium is the one that I work for, which deal with relatively low technology readiness level, which is aim for sort of like development of like a new technology, while DOE actually has another consortium called H2New, which is rather polishing up more high TRL level, and we are supposed to sort of like collaborate each other. And this low TRL level side research activity contains 4 different technologies. And we, as a cross-cut modeling, is working on sort of like the stitching all of those technology in terms of sort of like a very basic material property at low temperature and high temperature technologies, as well as the low TRL as well as high TRL technology. Let me skip this part, and probably most of the people are rather interested in the research that we did. Around 2010, I started to work on the hydrogen production research, which is about the 3-5 semiconductor and the water interface. And then this aforementioned this hydrogen consortium started 2016 and continues today. Earlier, our research was basically driven by John Turner at the National Renewable Energy Lab, who established highest solar to hydrogen conversion efficiency based on the gallium indium phosphide, and this is sort of like a demonstration video. This is from this year's outcome, but we are a hydrogen consortium, which consists of the NREL Sandia National Lab, and Lawrence Berkeley Lab, and Lawrence Livermore Lab, and Idaho National Lab. And those are the sort of like main steering committee members. And our research style is that we will have an internal collaboration. This is oxygen evolution reaction research that we published this year, as well as collaboration with universities. This one is University of Michigan and gallium nitride-based photoelectrode research. And then at the end, we have the DOE-BS Software Center, non-perturbative the studies of functional material and the non-equilibrium conditions. This project consists of basically the Lawrence Livermore Lab as a software development on the real-time time-dependent density function theory. And we have a partner at the Lawrence Berkeley Lab, and as well as SLAC. SLAC has a 2-component theory who works on the use of our simulation. And then we also have experimentalists, the Arnold Lindenberg work on ultra-fast experiment. The intention is to basically compare theory and experimental result to validate our software. And so we have activity on the develop open source software and the validation and the comprehensive software dissemination activities using lots of meeting and the summer school and the online tutorial. I'm gonna skip this, and progress so far is that we now have working real-time DTFT software, which is basically to simulate coupled electron ion and spin dynamics in the quantum mechanical level. Was that intention is to sort of like mimic time-dependent version of the Schrödinger equation, and which works on the currently already the GPU, and we demonstrated very good scaling. And this code actually is open software and available on this web page. I'm sorry, I took it from our review, but we have some scientific activities on the spin electron ion coupled system, and we successfully demonstrated that there are some interesting physics out of a highly excited system. And then we've been being engaged in lots of sort of like outreach. And because time is almost up, so let me summarize that. I'm repeating all of my activities, and I'm not going to repeat too much, but high pressure physics area on which continues to this CDAC collaboration with about sort of like 10% of my time, and then the non-equilibrium warm dense matter physics. And those are the sort of like related to CDAC, the collaboration. I'm hoping that we can resume a little bit more CDAC collaboration in the future together with Alfredo Correa. I hope he's listening to this talk. And other activity at the quantum simulation group is BS Software Center, as well as hydrogen production. That's a sort of like a rough research portfolio. And thank you for your attention.
Thank you for that wonderful tour de force review of your work. I'm sure there'll be lots of questions. Great to see the references to all of the earlier work as well, going back to Abrikosov. So questions for Tadashi, just unmute yourself or put the question in the chat.
Yeah, by the way, there is a...
Or raise your hand. Yes.
I just have a very general question about like the nature of your collaboration. I'm very fascinated by the different diversity of work that you have done, and also the application, like experimental collaborations, and I believe that's kind of facilitated by the National Lab environment, right? I'm wondering, because you work in like very different, like diverse, different level of theory versus computing and also the experiment. How does like a typical project like start? Like how in a national lab environment? Are there like I believe there are like groups, different groups, like theory groups and computing and experimental groups working on maybe similar problems. How do you guys get together and discuss and form this like big projects?
That's an excellent question. Typically, the NNSA type of project tend to be sort of like a top-down project, or somebody come up with sort of like a big science type of things, right? And then they assign people to this. And for example, this non-equilibrium warm dense matter physics was like that kind of a project. Actually, back then the Eric Schwegler was the one that who sort of like convinced me to work on it, and the reason was the previous director, Bill Goldstein, would like to see more activity on this ultra fast warm dense matter physics type of research using basically chopped pulse amplification, right? In this case, I do not have too much to say, so that as I mentioned earlier on, the first project on the board wasn't that successful, and from there, after lots of discussion, we try to steer things that the density functional theory calculation is more useful, right? The other one, If it is LDRD, it's up to you. You come up with some idea. But however, Livermore's LDRD is presumably something in alignment with the lab's strategy, which is basically defined by division leaders and the group leaders, so that you have to talk into those leaders to come up with, to align your idea to something that the lab would care about it. For hydrogen consortium, this is an interesting one that basically it's lots of talking that we have to sort of like define by ourselves based on our understanding about the mission of, let's say, HFTO, right, and our role, which is to help advancing low technology, the readiness level stuff. BS project probably last you are familiar with, but this is totally up to us basically. As long as you keep the good publication record within the sort of like area that you propose. So if you propose something which is very narrowly defined, then you'd be bound to your proposition, but otherwise you could do quite different things, except that, for example, say, if I work on something rather categorized as a warm dense matter physics or high energy density physics, based on this BS project, which is possible, by the way, we may get to complain from DOE that this is outside of scope. So otherwise, there isn't that much. So simple answer would be that NNSA projects tend to be like a top-down, so somebody would come and ask you, can you do this? But otherwise, in a way that we have to come up with the project where what you needed, you have to understand what certain specific organization wants you to do that, right? Which has a sort of like a broad sort of like a scope. Let's say if it is a CDAC, you would ask us, I'm thinking about this and that, and do you think it is good fit for CDAC? And then that's a way that you figure it out, right?
I see. Thank you very much. That was very helpful.
Thanks. Maybe I'll ask one. The work on boron, which was a CDAC collaboration in part, and boron-containing materials more broadly, was a fascinating and continues to be fascinating. I'm wondering what the current thinking is regarding the high-pressure superconducting phase that we found about 20 years ago at about 160 GPa. As far as I know, the structure was never determined or even predicted, at least in the early work. Is there current thinking about that? It's an 11 Kelvin superconductor by the time you get to 250 GPa.
That's a great question. I have a couple of ideas. Some may be boring, the other may be more interesting, but boring version comes from my observation about from other papers that I don't know, Russ, if you are familiar with or aware of it, but there are a few Japanese groups that who published a paper on lithium-doped alpha-rhombohedral boron, I believe that exhibited superconducting phase transition at high pressure. So in this case, what they, I think they performed the X-ray analysis or something, and kind of like they claim that they confirmed that there is no structural transformation. So it's even sort of like a band overlap would lead to superconducting phase. If that is the case, maybe structure doesn't matter too much as long as it starts to become metallic. Or the other version would be that this CMCA structure, if I understand correctly, that at least at the higher temperature side was experimentally confirmed, so that maybe either CMCA or its variant shows up in the very high pressure, which may be making it to the superconducting phase. So the former things, it may be just a coincidence because let's say that if this is a BCS type of a superconductor, and then the electron-phonon coupling becomes important, right? So it's not guaranteed that if structure is arbitrary, that whether it has a sufficient coupling or not. So that's something that maybe we should look into. For example, say, would disordered boron exhibit superconducting transition? In this case, it becomes a little bit hard because how we evaluate the electron-phonon coupling constant. But that's, oh, by the way, that's the type of things that right now we are not there, but this BS Software Center, NPNEQ, the software that developed under this project is supposed to be able to tell us something about the electron-photon coupling constant for the even not well-defined structure. As I mentioned, it's not there yet, but cross fingers that in the future we may be able to do it.
Oh, that's great. Thanks. More questions? Let's see. I mentioned the reference to Eprikosov in his important 1963 paper. That was a good one to cite. And actually, it's interesting that he wrote a paper in 1954, which stated that the high pressure molecular phase of hydrogen should be HCP based before it was much later named phase 1. So he really had tremendous insight into hydrogen as well as superconductivity. And of course, he his last few years were spent at Argonne, so was part of that community.
Right, right. It's amazing that sometimes you find this kind of like insight gained way before more the sophisticated technology become available.
Right. Okay. Comments or questions? Well, if not, thank you very much for an excellent talk. And we look forward to seeing everybody at the next webinar.
Thank you, Russ, and thank you, everybody.